Okay, John Allison, Arkansas Ames Math Director. I'm going to make another cold attempt. Y'all saw me if you looked at video number one. At 2025 released FRQs. I did this without looking at the problem beforehand, so I can kind of get a feel for how the students feel on this and see. They can see my mistakes. They can see that not everybody's perfect. Anyway, I made a pretty egregious error at the beginning of number one, corrected it before long, but took way too long working that problem. So we're going to see if we can work through this one a little quicker and make up some lost time. Here we go. I'm going to open the problem now. For the first time, look at it. And looks like, again, I don't show these because I don't want to violate College Board copyright restrictions, and you'll see the link to the problems in the video. You can open the link and follow along. So I got a shaded region R. This is for the A/B test, by the way. Shaded region R is bounded by the graph of the functions f and g. F of x equals x squared minus 2x, and g of x equals x plus sine pi x, as shown in the figure. And if you're following along at home, you can see this. Find the area of R. So g of x is the curve on top, and f of x is the curve on bottom. So we want the intersection. It's shown on the graph that the points of intersection are 0, 0 at the origin and 3, 3. So we're going to find for number 2a, the region R, the area of the region R is going to be given by the integral from 0 to 3 of g of x minus f of x times the differential dx. I'm going to go ahead and write the functions here. F of x equals x squared minus 2x, and g of x equals x plus sine pi times x. Make sure y'all can see my work here. This is the calculator portion of the exam. So I'm going to go to the calculator and enter those into y1 and y2. I'm going to do g of x in y1, which was x minus sine pi x. I checked earlier to make sure my calculator was in radians. Well, something is going on here. X, hit the wrong button on this online calculator. Plus sine pi times x. That's going to be my y1. And then my y2 is going to be x squared minus 2x. Oops. And I'm going to go ahead and delete y3 in the calculator right now. Okay, so now what I'm going to integrate in my calculator, I have y2 as g of x, and I have y1 as f of x, or y1 is g of x, and y2 is f of x. I'm going to integrate, get out of this, second close and quit, and math, do my integration on the calculator from 0 to 3. And inside the integrand, I'm going to put y1 minus y2 because I put y1 g of x. So, number 1 minus y2. And I can tell if I do the right order. I'll do this because it should be positive since I'm doing the upper curve minus the lower curve. And that gives me 5.13647. I can round up or chop. I'll go ahead and put 7. Go back to the problem, make sure there's no units to put on there. And there's not. Okay. So part B. says the region R is the base of a solid. For this solid, at each cross-section, at each x, the cross-section perpendicular to the x-axis is a rectangle with height x and base in the region R. Okay, so I'm going to go ahead and just sketch this graph really quick. This goes up like this. This goes down like this. This is the 0.33. This is the 0.00. This is g of x. This is f of x. I'm going to sketch this because I like to visualize this. The base of the rectangle is in that region R. This is the region R. I'm going to draw that base here. And we know that the length of that is g of x minus f of x. And it's a rectangle with height x. And the width of that rectangle, the base, is the differential dx. So I know now that I'm going to integrate these rectangles from 0 to 3 so that once I draw this, when I can see the math, I can do the math. I'm going to integrate from 0 to 3, find the volume of the solid, so I'm going to integrate. This is the volume of one cross-section. This is the volume of one cross-section. So I'm going to integrate all of those cross-section volumes. This is going to be x times g of x minus f of x, all times the differential. So I'm going to integrate that in my calculator. I'm going to go to calculator, and I'm going to go in and copy what I have. Oops. Getting a little button happy on my calculator here. Inside the differential, I'm going to insert an x and a parentheses so that I'm integrating x times g of x minus f of x dx. This is one cross-section. If I integrate all the cross-sections from 0 to 3, the volume, then I will have the volume of this solid. And so now we're going to integrate that, and I get 7.704, or rounded to 5 because it's a 9 after that. So it could be 4 or 5 here. I'm going to put units cubed. And up here I'm going to go ahead and put units squared. And that's the volume of that solid. Let's go to part C. Right, but do not evaluate an integral expression for the volume of the solid generated when the region R is rotated about the horizontal line y equals -2. So you can tell by the graph that this is somewhere in the neighborhood of -1 at this minimum. We can calculate that pretty easy since it's quadratic, and the vertex is going to occur at 1. So go back up here, it would be at -1. So that is 0.1, -1 at the vertex. So that's going to put -2 down here. So if we rotate this about the line, I think it's solid. I'm going to do the same thing here. If we rotate it about the line y equals -2, I'm going to be integrating this disk. It's going to be a large disk. I'm going to call this a large disk. When I rotate it around, and that distance is going to be g of x minus -2 is going to be 1 radius, because when I rotate that, it's going to look like this. G of x minus -2 is going to be g of x plus 2, and I'm going to subtract from that a smaller disk, which is going to be this rectangle, rotated about the line y equals -2. And that's going to occur when I do f of x minus -2 And so the washer is going to occur with the integral from 0 to 3 again. And this time it's going to occur the big disk minus the little disk. That's going to give me the washer. So it's going to be g of x plus 2 minus f of x plus 2, which, interesting enough, is going to subtract out the plus 2. And just make the g of x minus f of x kind of interesting. It's going to be pi r squared. That's what we're looking at here. So the volume of this is going to be pi times r squared. Pi times the radius squared. The volume of this is going to be pi times the radius squared. I almost made a big mistake there, didn't I? So I'm looking at the volume of the big disk minus the volume of the little disk. This is why I draw it out. I'm going to factor the pi out. And inside here, we'll put these here. I'll have the first. We could do it as two separate integrals. Where's the volume of the big one minus the volume of the small one? Or because of the, go ahead and do that. It's not the way most people teach it. It's not the way I usually teach it either. Or this is the way I usually teach it right here. There's a big disk minus a small disk. Oh, need my differential. I'm going to do it this way. That's the setup. And so now, let's go ahead and put that in the calculator. And this one's going to be pi times the integral from 0 to 3 g of x was my y1, so it is on plus 2, then square, whoops, that's not, I'm going to have to put it in parentheses inside there, square it looks like, dx, then I'm going to subtract pi again, times the integral again, from 0 to 3 again, I'm going to put parentheses, this is going to be f of x, which is going to be y2, plus 2, squared, and then dx, and that should give me the washer when I rotate this around. That's the volume of the big disk minus the volume of the small disk. And that's going to give me V equals V equals 92.22546. I'm going to go ahead and round because I've been doing that. This is going to be units cubed since it's volume. Make sure y'all can still see that. You can. Let's move up when I go to D though. All right, let's look at D. It can be shown that g prime of x equals 1 plus pi cosine pi x. Find the value of x from 0 less than x less than 1, at which the line tangent to the graph of f is parallel to the line tangent to the graph of d. So we are looking for f prime to equal g prime This is G prime. We know that F prime is a quadratic, so it's 2x minus 2. So we know these two have to be the same on the interval from 0 to 1. So that we can say that G prime of x equals F prime of x somewhere in the interval from 0 to 1. So I'm going to graph both G prime and F prime on my calculator. For my y equals, I'm going to go ahead and put and I'm going to put G prime, or sorry, F prime 2x minus 2. 2x minus 2. I'm going to graph those two and find where they equal on the interval from 0 to 1. All right, I'm not seeing it on the window I have, so I'm going to change my window. Oh, because I'm not looking from 0 to 1. That's why. Change my x values from 0 to 1. Okay, let's just graph that. All right, there's one intersection on the graph when I do that. So second trace intersect. First curve, second curve. And this happens when x equals 0.67546. I'm gonna round up to 6 because that's what I've been doing. So the tangent line, double check this to make sure I'm answering the right question. Both F and G are parallel. When x equals 0.676. And that should be number 2 solved. So, like I said, you'll find the problems linked in the description of the video.